Hi, today we're going to discuss about the Bernoulli Trial and the binomial distribution, and this is going to be the lecture 5.1. So if you remember, in the previous lecture we discussed about the expected value here, and we calculated the expected value, for example, for this random variable, where x is going to be the number of the hats when you toss the coin 3 times. And we figure out this formula of calculating the expected value and the variance for such a random variable. So when you toss the coin 3 times, so you might have different scenarios. So what we need to do is we need to count the number of the hats. For example, you might get no hats at all. So you toss the coin 3 times and you get the 3 tails. It's going to be tails, 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 and no hats. So in this case, the number of the hats is going to be 0. And the probability of this scenario is equal to 1 over 8. And at the same time, it is possible that you can get only 1 hats, right? So there are 3 different scenarios of getting 1 hats. Either hats, tail, tails, or tails, hats, tails, or tails, tails, hats. And the probability of each of the cases is 1 over 8, and the probability of total is going to be the sum of the 3. So that is why the probability of obtaining 1 hats is 3 over 8, and so on. So in order to calculate the expected value, we need to multiply always x to the probability, then sum them. So we calculated the expected value is equal to 1.5, and at the same time, in order to calculate the variance, we've calculated the expected value of the x in the square, and the expected value of the x in the square is equal to 24 over 8, and we can calculate the expected value of the x in the square by just multiplying the x in the square to the probability of the x. Okay, so in this formula we've obtained the variance and the expected value, and which is important for us in this lecture is this process when we are counting the number of the hats, when we have 2 outputs. So it appears tossing a coin is not only a case when we are going to have the 2 outputs. So it appears there are many different situations in our life when we can categorize the output into the 2 different categories. Like you can say that success or the failure. For example, I can choose a student who's going to be a female or not female. Or if you have lots of cards in the deck of cards, you can say that, hey, success is going to be choosing a card which is going to be the ace, and the failure is going to be the probability of choosing or the card which is not the ace, and so on. So you can always categorize many different experiments into the 2 different categories, like a failure and success. So this kind of the experiments and this kind of probability of random variables are important, and they're going to be called as the Bernoulli random variable. And again, so suppose that a trial or the experiment where the output can be only 2. And we are going to call those outputs as the failure or success. And we usually denote the outputs again as a 0 and 1. So 1 is going to be one is going to be denoted as success, and the 0 is going to be denoted as the failure. And we are also given that the probability of obtaining success is equal to the p, so this is some notations about the Bernoulli trial, and the probability of obtaining failure is going to be equal to the 1 over p. For example, let's assume that when you toss a coin, getting a hat is success, and getting a tails is failure. So in this case, the probability of success in the failure is equal to the 1 over 2. But you can do this in this way. For example, let's assume that you would like to roll a die, and there are 6 different outputs. And let's assume that if you get 1, this is going to be the success, and if you get any other value, it's going to be failure. So in this case, probability of success is 1 over 6, because only in one case you've got the success, and the probability of failure is going to be 5 over 6. So we are going to talk about this variable. We're going to combine this trial in many different ways, and we're going to talk about the 2 different important probability distributions. So one is called the binomial distribution, another one is called the geometric distribution. But talking about this variable, it is called the Bernoulli random variable, which is named after the Swiss mathematician James Bernoulli. So again, so the Bernoulli variable means that it can take only 2 values, and you can decide how to denote this. So here we decided as either 0 or either 1, or you can decide like either 2 or 4, it doesn't matter. And the important is it can have only 2 outputs, and the probability of 1 is equal to the p, and the probability of 0 is going to be 1 minus p, because the sum of the 2 probabilities should be equal to 1. Suppose that now we are going to do n independent Bernoulli trials where each of the result is going to be either success and a failure, and the probability of success is p, and the probability of failure is 1 minus p. And now, do you remember in the beginning of the lecture, we've considered an example where we counted the number of the heads, or essentially when we counted the number of the successful trials, right? So this is very important random variable when we are going to count the number of the successful trials, out of n trials. So if you are going to do this Bernoulli trial with 2 outputs, not once, but many times, and how many of them you're going to get success, right? If you toss the coin 3 times, and how many of them you've got a heads? Do you see that this is the really important question? And let's assume that the x is going to be the random variable, which is going to denote the number of the successful trials out of n trials. And it appears it usually comes with the 2 attributes, 2 parameters, n, because it depends really the number of the trials. So for example, obviously probability of obtaining 2 successful trials in 3 trials is higher than obtaining 2 successful trials out of, let's say, 15. Okay, so obviously the n is important, the number of the trials, total number of the trials is important, and also the p, the probability of obtaining a single successful trial, is also important. So we call this random variable as the binomial random variable. In the first part of the lecture, we're going to discuss about this random variable. So before we discuss the probability mass function for this kind of random variables in general, let's solve this kind of problem. So let's say x is going to be the number of the goals shooted when you kick a penalty 3 times. Probability that 1 time when you shoot a penalty, you will concede a goal, so you will make goal, is 0.6. Okay, so it means that if you've got a penalty kick, so probability that you will make the goal is 60%. Now you're going to kick the penalty 3 times, and I would like to know what is the number of the goals you can make. Well, if you're kicking the penalty 3 times, you can make no goals at all, right? Because all of the 3 times you could get unsuccessful trial, or you can make 1 goal, or you can make 2 goals, or you can make 3 goals, right? So all of the values of the x, the number of the successful trials, right? So if you're making 3 trials, the number of the successful trials is going to be either 0, either 1, 2, 3. This is going to be our random variable, and what we would like to do is, we would like to get the probabilities. And then by just solving this problem, I would like to figure out the general formula for finding the probabilities in binomial distributions, or essentially the mass function for the binomial distribution. So let's calculate the probability of obtaining no goals at all. So x is equal to 0 simply. So when x is equal to 0, so x is equal to 0, it means that you need to get 3 failures in a row, right? So basically it's going to be, so let us denote the failure as a q. Okay, so 1 minus p can be denoted as a q. 1 minus p is going to be denoted as a q. So it should be q times as a q times as a q. And that's going to be equal to 0.4 in the q. At the same time, probability that x is equal to the 1 is equal to all the cases when you're going to make 1 goal out of 3, right? And it is possible to do this in the 3 different scenarios. So for example, you concede a penalty, you make the penalty as a goal, you make a goal out of penalty, and then twice in a row you're going to get failure, so to make the goal. Okay, so exactly this scenario: goal, no goal, no goal. Okay, or the total number of the goals is equal to the 1 can be obtained using a different scenario. For example, the q PQ, or you can obtain this as the QQP, right? And 3 different scenarios, or in this scenario, or in this scenario, or in this scenario. Please know that in all of the scenarios, the probabilities are the same. So the probability of the PQQ, or QPQ, or QQP are the same. Okay, so in total, so our goal is not to solve this problem simply. Our goal is to solve this problem, and by solving this, derive a general formula. Okay, so when x is equal to the 1, it means that it should be only one p, right? Because always we're going to get the probabilities multiplication of the p and q. Okay, and the only question is how many p's should be participated in our general formula of the probability, and how many q's. Obviously, the number of the p's is going to be equal to the x is equal to the 1, right? Because we are calculating the probability of getting one success, so that is why in our probability formula there should be only one p participated, right? It should be 1 times p and 2 times q. It should be always p, q, q. The only question is how many different scenarios it can be obtained, right? So in this case, it is equal to the 3. Okay, so let us try to consider this for the x is equal to the 2, and maybe we can figure out how to get this number 3. So when x is equal to the 2, when x is equal to the 2, there are again 3 different scenarios. So it means that there should be 2 p's, p, and 1 times q, right? This is for sure, because q means that in 2 of the trials, I've got the success, in 1 times I've got a failure. Okay? And the only question is, in how many different rearrangements we can do? Right? Okay, because the multiplication is always the same, right? So the multiplication is going to, so this multiplication, and this multiplication are always going to give you the same result. So the only question is, how many different rearrangements are possible of this sequence of the p's and q's? Okay? So let's do this. So it is going to be p, q, or p, q, p, or q, p, p, right? So there are 3 cases. Okay, and the probability of x is equal to the 3 is going to be only one case, there is only one case when we're going to multiply p, and p. Okay, and the number of the rearrangements of the 3 p's is just simply 1. So we can simply fill out here, it's going to be q in the cube, 3p q in the square, 3p squared q, and the p in the cube. Again, the only question is how to get the 3. Okay? Or what does it mean, the 3? Did you already figure out what does it mean, the 3?
3 items.
3 items. No. Actually, the 3 is the number of the rearrangements of the 3 letters. Right? So you've got 3 letters. You know why you've got 3 letters? Because n is equal to the 3, right? You are trying this experiment 3 times. And a number of the rearrangements of the 3 letters is equal to the 3. Okay? And if you remember, we've learned about the combinatorial analysis that the number of the rearrangements of the 3 items is equal to what? What is the number of the rearrangement of the 3 items? It's 3 factorials. Right? If all of the items are different. But here we've got 2 items are the same. For example, this q and q are the same, and just rearranging them is not going to give us the new combination, right? So it should be equal to the divided to the 2 factorials. Okay? So that is why what we get is simply 3. The same is here. So we need to rearrange this. There are 3 rearrangements here. So it should be 3 factorials divided to the 2 factorials. So that is why it's equal to the 3. Okay? So it should give us some insights about deriving the general formula of the binomial distribution. So I would like to know, hey, if I make this experiment n times, what is the probability that I'm going to get exactly k successes? So this is our question. So I would like to continue with this question, with this problem, and create the table where we have to, this is all the results of those calculations which we did before. And please note that the sum is equal to the 1. Okay? So here, for n is equal to the 4, I don't want to now to do all of these cases. I would like to derive the formula. Okay? So, for example, what is the probability that x is equal to the 2? So I hope that you understand what does it mean this n is equal to the 4, k is equal to the 2, and so on. Right? So n is equal to the 4, it means that we concede we are going to make our experiment 4 times. Okay? 4 times we try. We try to kick the penalty. In this case, in this particular case, to kick the penalty. And every time when we kick the penalty, probability that we will make the goal is 60%. Okay? So if I would like to know what is the probability of x is equal to the 2, it means that what is the probability that exactly 2 of these 4 trials, I will get the goal. Right? So what does it mean? I need to get twice the success. I need to get P and P, and 2 times the failure, Q and Q, right? So I'm not asking you what is the probability that I will make at least 2 goals, or at most 2 goals, right? I'm asking you what is the probability of making exactly 2 goals, okay? So that is why in your sequence of P's and Q's, there should be exactly 2 P's and 2 Q's, okay? This is for sure. So now what we have to do is we need to figure out the number of the rearrangements, right? So what is the number of the rearrangements?
4 factorial divided by 2 factorial.
4 factorials divided to the 2 factorials divided to the 2 factorials. Right?
Yes.
Okay. So in general, if you make n experiments, so let's say 1 experiment, second, third, fourth, and so on. So many n experiments. What is the probability of obtaining exactly k successful trials? If we would just generalize this case, okay? So let's talk about, again, the number of the P's and Q's. The total number of the P's and Q's should be equal to the n, right? Because you're making the n trial, every time you can get either P, either Q. But in total, you need to get exactly n P's and Q's in total, right? Okay, so but at the same time, I know that exactly k of them should be P's, right? So here I need to get the P, for example, here I need to get the P, here I need to get P. So the number of the P's is equal to the K. So because the number of the successful trials is equal to the K, right? There should be P in the power of K. So it should be P in the power of K times, and the number of the Q's is, Q is going to be simply n minus K, because the rest should be Q's. Right? The only thing is we need to figure out, again, the number of the rearrangements of this piece in Q's. The number of the rearrangements is n factorials divided to the k factorials multiplied to n minus k factorials. It is going to be n factorials divided to the k factorials multiplied to n minus k factorials. According to the rule which we discussed, the number of the permutations when some items are alike. Right? Here I've got k items which are the same, KPs, and then minus K items which are also the same, like Qs. Okay? So this is going to be the general formula for the binomial distribution, and actually it is not so difficult to understand. Like, it is difficult to accept this probably because it is super long, but it is also difficult to derive this. So I've just substituted the K was the X, but it is the same. So probability of obtaining K successes. So let me make it K so that it should be less confusing. So the K successes out of n is going to be C n K, P in the power of K, Q in the power of n minus K. It is equal to the K n factorials divided to the K factorials divided to the n minus K factorials, P in the power of K, Q in the power of n minus K. Okay, so we are going to do a couple of exercises. So let's start with this one. A bag contains 10 chips. 3 of the chips are red, 5 of them are green, 2 of them are blue. 3 chips are selected with replacement. It means that every time I choose this, I'm going to put this bag, replace this bag. So for the probability that you select exactly 1 red chip, if you're selecting 3. Okay, this is exactly binomial distribution, right? Because you're making the fixed number of the trials. So in this case, you're making n is equal to the 3 trials. Right? Because you're going to select the 3 chips, right? And then probability of success. What is it? So I'm going to categorize again the output. Okay, so obviously if you choose the chips, there are 3 different colors, right? So the blue, green, and the red. But I'm going to make this categorize this: red or not red, success or failure. Okay. So what is the probability of success? So in this case, probability of choosing a red chip. So this is 3 over 10, right? And the probability of the failure is equal to the 7 over 10. Again, so in this case, either we are evaluating this probability of choosing the red card or not red chip, the chip. So what we need to do is we need to use the binomial formula, right? So we need to find the probability of K is equal to 1. Or according to this formula, X is equal to the 1. What is the probability of exactly 1 red chip when you're going to choose the chips 3 times? right? And I'm just going to substitute this to here. It is going to be equal to the C 3 1, P in the power of 1, Q in the power of 3 minus 1. According to this formula, just according to this one, right? So this is going to be equal to the 3 factorials divided to the 1 factorial multiplied to the 2 factorials. I'm just expanding this formula of the C times the P times the Q in the power of 2. Okay, so you can just put all of these numbers to make the calculations. So 3 times P is equal to the 3 over 10, and the Q is equal to the 7 over 10 in the square. And you can easily make those calculations using a calculator. But again, so you can solve this kind of problems using just one formula of the binomial distribution. Well, the binomial distribution is very important because we can get this kind of distribution in many different situations in our life. Let's solve the problem. It is known that screws produced by a certain company will be defective with a probability of 0.01. So the company makes the screws by 10, so it produces the packages of the screws, and it has the money back guarantee that at most 2 screws out of 10 is defective. So what does it mean? It means that the company produces lots of screws, and if you choose one of the screws at random, probability that this screw is defective is 0.01. So it means that at most, like 1 out of 100 screws are defective. So now, so the company just makes the 10 screws, 10, 10, 10, and puts the pack and sells this to the customers. And if the customer opens this and it finds 2 screws defective, or 3, or even more, the customer can come back to the company and get the money back. Okay? So if 1 screw is defective, then it's okay. So what we need to do is, so the company produced lots of packages, like millions of the packages of the screws. And if I choose one of the packs, what is the probability that for this pack, the company should give me the guarantee back? Okay, so let's calculate this. Or what is the probability that this pack with 10 screws has more than 2 defective screws? So let's calculate this. So in this case, what we need to do is, actually this is exactly the binomial distribution, where n is going to be the number of the trials is equal to the 10, so because you've got 10 screws, right? Probability that one of the screws in your package is defective is the same. It's always the same, 0.01. Okay? Probability that one of the screws is defective, 0.01. Okay? And the probability that this is not defective is 0.99. And now, what you need to do is that the x, which is going to be the number of defective screws, has the binomial distribution, is the binomial variable. And we can easily use the formula for that. So what we need to do is we need to find the probability of x is more or equal to the 2. So again, probability that you choose the pack which is going to have 2 or more defective screws, right? This is what does it mean? Probability of x is more or equal to the 2. So this is equal to p of x is equal to the 2 plus p of x is equal to the 3 and so on, plus p of x is equal to the 10. Right? Because x can go from 2 to the 10. And it's a difficult process, right? Because you need to calculate so many probabilities. But fortunately for us, we know how to work with the complement of the events, and we can write this equation as the 1 minus probability of x is equal to the 0 minus probability of x is equal to the 1. Because we know that if you just take this part and put this into this part of the equation, you're going to get simply the sum of all of the probabilities, right? So you're going to get p of 0, 1, 2, 3, 4, 5, and so on, and 10, and it should be equal to the 1, for sure. Okay? So, and if I just need this part of the probability, I don't need to find all of them. So I can find the probability of x is equal to the 0 and 1, and subtract this from the 1. So let's calculate this. So what is the probability of x is equal to the 0? It is the combination of the 10 and 0. P should be 0, Q should be 10, minus the combination of the 10 and 1. P should be 1, Q should be 9. Okay? And just by substituting all of the values of the P and Q, we can calculate this probability. Okay, so this is going to be the probability of choosing one pack for which the company should pick the money back. Okay, so here are the examples of the binomial distributions, and it appears we can calculate the mean and the variance of the binomial distribution using these formulas. So here, the mean is calculated simply by just multiplying the number of the trials to the probability of successful trials, and the variance is going to be calculated as the n, p, and q. Okay, please note that 1 minus p is denoted as the q. What does it mean? It means that, for example, if the probability of making a goal when you kick a penalty is 60%, I'm asking you, hey, what is the average number of the penalty, average number of the goals you're going to make out of 10 penalties, right? And this is kind of intuitive that this is equal to the 6, right? So 10 times to the 0.6. Okay, so this is what does it mean, the expected value. Or for example, if I say, if the probability of choosing one screw which is defective is 0.01, right? So what is the number of the defective screws I should expect when I have 100 screws? It should be 1. So the n times the probability of success, okay? And the variance is going to be calculated as the NPQ, so we're going to use this value, or use this formula for the variance, in order to make the comparisons again. So let's make one more exercise. So a Gallup poll of 1,236 adults showed that 14% believe that bad luck follows if your path is crossed by the black cat. So taking this record into consideration, could you please tell me what is the expected number of the people who would believe that this poll would be done with a much larger sample? Okay, so in a small sample of only 1,236 adults, so 14% believes that bad luck follows if your path crossed by the black cat. And if I just increase the sample from 1,236 to the 2,800, what is going to be the number of the people who believe this? Or which number of the people, adults, we should expect who would believe this, right? So in this case, what we need to do is we need to look to this poll as the binomial distribution. So what we did is we went through 1,236 adults and we asked them whether they believe to this or not. Okay, so again, this is like a two categories which they have to answer. Either they believe, either don't. Okay, and 14% believes means that probability that I will choose one of them and it is going to be the person who believes to this is 0.14. So this is what does it mean? You see, so here it is given as a proportions because the proportion of the people who believe to this is 14%, but proportions and the probability of success is more or less the same thing. Okay, we're going to discuss about the proportions a little bit later, and the Q is going to be equal to 1 minus P, which is equal to 0.86. Okay, and now what you ask is, so if you would just increase the sample from 1,236 to the 2,800, what would be the number of the successful cases? So in our case, what would be the number of the people who would believe to this? Okay, in average. So in order to do this, so the expected value of this, E of x, is going to be equal to the n times the p. In our case, it's going to be 2,800 times the 0.14. Okay, and that's going to be the number of the people we expect they are going to believe to this. So this is our last example which we considered. So we are going to start talking about the geometric distribution in our next lecture. Thank you very much for your attention. I hope that this was helpful for you. What is the probability that this pack is going to have